Hello everyone, this is Bharat Singla and welcome to CodeChef. This is the one-stop destination for you to master competitive programming. Great, so let's get started. Welcome back everyone. The problem we'll be discussing is square function from the August first starters. Difficulty kinda easy to easy medium and there are prerequisites. So it is basically not for beginners and the prerequisites are math, good knowledge of math and prime factorization using the smallest prime factor, which is a safe modification in which you can prime factorize a number in log n instead of square root n. So if you are well versed with them, let's jump straight in. So the problem is as follows, that a function fx is defined as x by y, where y is the maximum perfect square that divides x. For example, the maximum perfect square that divides 12 is 4, the largest one. So f of 12 is nothing but 12 by 4, which is 3. In case of 36, it itself is a perfect square. So f of 36 will obviously be 36 by 36, that is 1. So for any perfect square, f of a perfect square is nothing but 1. And then we have another example 7, which is a prime number. So in this case, it will be 1. So 7 by 1 is 1. Now what we have to do is you're given an array A of n integers. Find the number of unordered pairs I comma j such that f of ai times aj is greater than 1. So clearly the problem can be modified as such that find the number of pairs where the product where f of ai into aj is equal to 1, right? And from total number of pairs for given n we can subtract that, right? So that way we'll get this. So we know that when is f of x equals to 1, that is when x is a perfect square, like in case of 36, right? So basically now let's move on to the approach. So basically the problem boils down to finding the number of pairs such that a number of unordered pairs I comma j such that ai times aj is a perfect square. Fine. So if this product is a perfect square, then that is a valid pair. And from the total number of pairs, if we'll subtract that, then we'll get what is desired from the problem. Okay, so this is very simple. The solution is not simple though. For now, I want you to leave this problem. Answer me a simpler sub problem that is given an array. Say for example 2, then 5, 3, 5, 5, 3. Find the number of pairs such that the elements are equal. So this is very insightful for the original problem, and I want you to completely forget that, because if you do not understand this, it will be really hard for you to understand the solution for the original problem. So how do we do this? Well, we can separately add the number of ways, the number of pairs in which I get 5, right? This is one pair, then this is another pair, and this is also a pair, right? So these are 3 pairs. Then for 2 we do not even have another 2, and for 3 this is one pair, right? So what we can do is clearly we can form a frequency kind of thing where 2's frequency is 1, right? 5's frequency is 3 and 3's frequency is 2, right? And from this all we have to do is sum up all the frequencies C2. So the number of ways in which you could select pairs such that they are both equals to 2, that is 1C2. For 3 such that both of them are 5, that is 3C2. And for this you have 2C2, right? Exactly what is given by these pairs, right? So this is nothing but 0, this is nothing but 3, this is nothing but 1, right? Exactly what is given by that drawing I made. So basically we can treat them separately and choose 2 will give us the number of ways in which we can select a pair. Finally, summing up 0 plus 3 plus 1 will give me 4, and yes, here I can form 4 such pairs. So this is a simpler sub problem, and the way this works is by finding frequencies and then using C2 to get the number of pairs. Great. Now that you understand this, let's move on to the original problem. So we have, when is the, ask yourself, when is a number a perfect square? So this is when the prime factorization of the number n looks something like 2 to the power alpha times 3 to the power beta, 5 to the power gamma, so on. Right. So this is the general prime factorization of a number, and n is a perfect square when alpha plus alpha, beta, gamma all are even. Right. This is pretty elementary maths. So all we want is the power of each prime number in n to be even. Let's extend this further, that when is the product of two numbers a and b, a times b, so when is this equal to a perfect square? So if say a's factorization looks something like alpha, beta, gamma, so on, and b's prime factorization looks like 2 alpha dash 3 beta dash, so on, right? So whatever it is, okay, that doesn't really matter. What matter is if the product is a perfect square. So in the product also, similar to this, right, the power should be even. All the power should be even. So this means that the power of 2 in a times the power of, say, this is 2 to the power x, this is 2 to the power y. So if there, when is, so what is basically the product of these two? So this is x plus y, right? So we want that the power of 2 in A times the power of 2 in B, that should be even, right? Their product should have all the powers even. So this means that x plus y should be even, meaning that if both x and y are even, right? So both x and y are even. In that case, there the when we do the product, the power will be even, right? Because the sum of two even numbers is even. Or if both x and y are odd, in that case also when we'll do the product, the power of that prime number will come out to be even. Fine. For example, 5 to the power 2 times say 7 to the power 1. This is the original number, right? This is, for example, this is A, and B is 5 to the power 1 times 7 to the power, let's say, 3. So when we'll do the product will be nothing but 5 cube times 7 to the power 4. So since 1 and 3 both were odd numbers, in the end this will be even, and since one of them was even and one was odd, this comes out to be odd, right? So their product will not be a perfect square. For each of the numbers, odd and odd should match, even and even should match. Basically basically now taking this a bit further, is that even plus odd is odd, even plus even is even. So even does not make any difference to the parity. So even can be simply ignored. So what we'll do is we will first kind of find the prime factorization of a number. So basically notice that 5 to the power 2, right, does not make any difference when it will be multiplied, right? Because this will not change the parity of the other power of 5 in the other number. So even powers can simply be ignored. All that should be left is are the ones with odd, right? So for example we have the number 360. This is a random number. So this can be written as 2 to the power 3 times 2 cube times 3 square times 5 to the power 1. This is 8 times 9, that is 72, times 5, that is 360. Fine. So this is the prime factorization of 360. Now notice when 360 will be multiplied by some number, will, so for example that has something like 3 to the power x and so on. So does these two, when 2 plus x will be there, will 2 make any difference to the parity of x because 2 is even? No, it won't. So I can simply, what I can do is remove this. So in the end all we have is 2 to the power 3 times 5 to the power 1, and here also only the parity matters. So we can represent 360 as a specialized prime factorization of a set of 2 and 5. denoting that 2 and prime 5. Remember this very carefully. 360 can be written in a way as a set of 2 and 5, denoting that 2 occurs, 2's power in 360 is odd, and 5's power in 360 is odd. All the other numbers, all the other primes are occurring even number of times. 7 and all are also occurring even number of times, that is 0. 3 occurred, 3's power was 2, it was 9, right? So 2 was even, so we ignored it, right? So that's how 360 can be written. Now notice that when will 360 with some other number form a perfect square? Well, now it is pretty simple that its specialized set should also be exactly the same. For example, the numbers with such set are 10, right? Because 10 is 2 to the power 1 times 5 to the power 1. So 2 and 5 are the odd prime numbers. So, and notice that yes. So what will happen when we product 360 and 10? So what will happen is 2 and 2 will get multiplied. So 2's power was something odd, and in 10 also 2's power is something odd. Their product will make 2's power something even. So that works. For 5 also, its power will become even, so that works. And for all, if the powers become even, the product of the numbers is a perfect square. And indeed, 360 into 10 is equal to 3600, which is 60 square. So all the numbers with same set, because even can be ignored, right? If here, for example, 7 would have occurred even number of times, so it was 7 square also in the number, or 7 to the power 4. That wouldn't have made any difference to the parity, right? That could be simply ignored because that is not causing any issues and not making it not a perfect square, right? So all the numbers with even powers can be excluded. Great. So remember that sub problem. Each of the numbers of the array can be converted into its specialized set, and then all we have to do is again count the frequency of those sets and then do NC2, because only those whose product will make a perfect square. So let's move on to the code. Problem is really good, very simple problem, really complex solution, but very easy and nuanced. So this is really educational and I want to make the video as equally educational. So I'll be coding it out from a blank slate. So let's start off the implementation. So we have the basic here, and what I'll do is first take the input for the test cases and call a function solve. So before that, to do the prime factorization, we'll need to build that SPF algorithm, the sieve. So let's create a constant int n, right? That is 1 is 6, and this I get from the constraints. The maximum value of ai could be 1 is 6, and let's create a vector of int SPF of size n plus 1 filled with -1. SPF of I is the smallest prime factor that divides I. So if SPF of I is equals to -1, so if it currently is a prime number, then like this is the prerequisite. I won't be explaining it in much detail. You can read about it first and then come back here. Cool. So I want all the multiples of I set it as its SPF. Fine. So that's how I built this array. And now let's implement the function that will return all the odd factors. So that set I was talking about. Okay. So first find the prime factorization. So map of int and int is nothing but a number and its power, right? The true prime factorization. So while n is greater than 1, what I say is that factors of SPF of n I can increment, right? Its power is now 1 more than what it was. And basically, for example, I'll show you n divided equals by SPF of n. Cool. So if the number, for example, was say 12, so what will happen is that 12's SPF is 2, so I can say that 2's power now becomes 1, right? It was 0 initially. In a map, it's 0, so it becomes 1. Then 12 becomes 6. So you divide 12 by 6. Then you go to 6. For 6 again, the SPF is 2. So 2's power now becomes 2. You increment it basically. And then the number becomes 6 by 2, that is 3. Now n is 3 for n. For 3, SPF of 3 is 3. Right? So you increment 3's power also. So 3 is also there in 12. And now it becomes 1, and here we can stop. So in the end, I'll have it something like 2, whose frequency is 2, and you have 3, whose frequency is 1, and that is exactly the prime factorization of 12. That again is a prerequisite, I just briefly explained it. Now let's create a set of int odd factors, and now let's iterate on the map factor and power. I check if the power is odd. In that case, in the odd factors, I insert the factor. Fine, so all the factors with power odd, the one we wanted, and we can simply return this, right? And notice that because set is ordered, so 3 comma 5 comma 1 will be converted to 1 comma 3 comma 5, right? So in the end, matching will be easier. Cool. So yes, that is the function for odd factors. Now let us implement the main logic. So the solve function. So first we have n. Then what we do is we take the input for n, right? We take the input for the array, but notice that an array is not required. In the end, what matters is the frequency of the factorization of that number. So what I'll say is the frequency of get odd factors of x increases, and finally we just have to find the NC2 of same specialized factorizations. So you can have int answer equals 0, then you go on all the you iterate on the frequency. So temp doesn't really matter, and the frequency. This is what we'll be doing an NC2 on, right? So we go on the frequencies, and what I do is answer plus equals to NC2 of frequency. Fine. So first let's create a frequency map that maps the factorization to an int, the frequency. Cool. And now we can simply output total number of pairs minus answer. That is NC2 of n. Total all the possible pairs minus those that give f of ai into aj a perfect square equals 1 basically. And if we subtract that, we get the ones that give greater than 1. That was asked in the problem. Cool. So yes, that should work. One thing that we have forgot to implement the NC2 function. Cool. And okay, so one another thing is that this is of the order n square, and n could be as big as 1e5. So this clearly exceeds the range of int. So best is to just define int to long long. Fine. So everywhere my code replaces int with long long, but that causes issue here. So this could be converted to this or signed main. So because this int also got replaced with long long, and main must return int only. Fine. So let's recap what we did. We first created the SPF array. Then we took the input for test cases, and we took the input for n. We maintained the frequency of all the factorizations. Basically, if we replace all the numbers with that set of odd factors, right, and then find the frequency and taking NC2, we get all the number of pairs. That's exactly what we are doing here, right? And then I find the NC2 and all, and from the total number of pairs, if I subtract the unwanted, I get the wanted. So get odd factors works like finding the factorization, then finding all the factors, prime numbers an with an odd power, right? So yes, finally we'll get our answer, and let's quickly run it. So let's see what we get. So we get 253, and I guess this is correct. Such a long code, not expecting to get it right in the first try. So yes, it is 253. So let's quickly copy it, take the leap of faith, hit the submit button, and hope for an AC. Till then, one thing I want to show is that Unacademy takes live session. CodeChef educators take live session at Unacademy and teach you DSA and everything related to the world of competitive programming. So if you want to learn from the best in the world, ICPC World finalists, IOI medalists, 6-star, 7-star coders, then make sure to opt for the Unacademy Plus subscription, and you'll also get an access to the Discord community, problem sets for each topic, 24/7 doubt solving. So what are you waiting for? The best investment you can make. And don't forget to use the code Bharat27 to get an instant 10% discount on your subscription. Great. So let's check. And yes, we did get an AC. Hope you liked it. It took me a lot of effort to write this in front of you without any errors. And yeah, this was it for this video. If you liked it, make sure to like it and leave down any queries in the comments, share it with your friends, etc. etc. This is Bharat Singla from CodeChef signing off for now. I'll see you next time.